Welcome to lecture 45 on electrical machines 1, and we were discussing various connections of three phase transformers and gave you a sort of guideline when to select what connections. Okay, star delta, delta star or zigzag, and zigzag connection, as I told you, is essentially a star connections, and in my last class I told you, because with delta connection I just drew one digit 0 and it was like this, and I told you if you know the input line to line voltage and the turns of each primary and each secondary coils, then you will be able to calculate what will be the phase voltages of these zigzag connections between the neutral and one of the phases of the output. This goes to load A, B and C, and what is the line to line voltage and phase voltage, how to calculate, we can easily relate them. Okay. Now, another interesting thing with transformers is that using transformers, it will be possible to convert a given polyphase system to another polyphase system, that is called phase conversion. We will briefly discuss that phase conversion, of which one very popular connection is called Scott connection. Which changes a given three phase voltage, it converts to a three phase balanced voltage, of course, to a two phase balanced voltage. See, our supply system is all three phase: generation, distribution, transmission. Then of course, you get single phase voltage, you can get between one line and neutral, like that. That is there, but sometimes two phase balanced voltage may be needed. For example, if you have a two phase induction motor, okay, then you must supply the stator coils by a two phase supply instead of a three phase balance supply, because the motor is two phase, and two phase induction motors are also used in control system and other applications. There similarly, there may be two phase electric furnaces where two phase supply is necessary. But the problem is, first understand the problem. Problem is you have a three phase supply available to you, AS, BS, CS, and maybe with a neutral NS supply is available, and you have a two phase load this side. So, how to convert this three phase supply to a balanced two phase supply voltage system and then feed your load? That is the problem. So, the connection is called Scott connection, and it uses two single phase transformers, two numbers of single phase transformer. That is, three phase to two conversion requires two single phase transformers, separate transformers. and you can show that it will give you a balanced two phase voltage. The idea is very simple. Okay. So, let us start. What is done is this, you have one transformer whose primary coil, I will say, because transformers are to be named. In case of 3 phase case, 3 isolated transformers can be used, and there were 6 coils. So, proper naming is required. So, in this case of course, 2 transformers are there, and let us call this transformer to be transformer A with terminals A 1 A 2, and its secondary is having B 1, oh sorry, small letters B 1 B 2, A 1 A 2, sorry, small A 1 like the 3 phase A 1 A 2, and you have another transformers which I am drawing horizontally, the reason will be clear, and its secondary is this one. Okay. This is suppose B 1 B 2, and this is also B 1 B 2. Okay. Now, we require 2 transformer, one transformer is transformer A, another transformer is transformer B. Now, are these 2 transformers are identical? Really not. What happens is this, you select these 2 transformers in such a way that the secondary turns are equal N 2 N 2. Okay. And primary turns of this transformer is B transformer is N 1. So, secondary turns are same, primary turns of transformer B is equal to suppose N 2. Then primary turns of transformer A should be, this is, let me write why I have written N 2, N 1, primary turns N 1, these 2 are N 2 N 2 secondary. So, N 1, and then this primary turns are selected at root 3 by N 1. That is, the primary turns of this is root 3 by 2 N 1, its secondary turns N 2, primary turns of this transformer is N 1, and its secondary turns is N 2. That is how the transformer turns you have to select of these 2 transformers. Okay. And not only that, then in transformer B primary at the 50% you must have a tapping, such that this turns becomes then N 1 by 2 and this turns becomes N 1 by 2. So, total turns is N 1. So, at 50% there will be a tapping. Okay. Now, what you will be doing is this A 2 you join it here with this 50% tapping, and this 3 I will connect it to supply A 1, say this I connect to B 1 and this I connect to B 2. Suppose I connect like that, and secondary I have not connected anything, it is just isolated and living like that. Now, first of all you can see that what is the voltage applied to the primary of transformer B. the voltage applied is line to line voltage, is not, and total number of turns is N 1. Mind you, this transformer has its own magnetic circuit separate, this transformer has its own magnetic circuit. So, volt per turn of transformer B is equal to V L L by N 2, N 1, total turns is N 1, V L L voltage per turn. Therefore, what will be the induced voltage between in the secondary of the transformer B? So, voltage magnitude V 1 V 2, it will be volt per turn of transformer A into N 2, what else? So, this voltage will be N 2 by N 1 into V L L. Clear? Okay. Now, you see, I will draw here so that I do not have to, or shall I go to next page? I will select this one, this diagram is needed. So, select this, so that I do not have to draw. Copy and I go to next page and paste it. Okay. So, that is the thing. Now, I will erase these things. So, this was the thing. Acha. Now, and we have examined what is this. Now, suppose I want to see in phasor terms what are the voltage I have applied on the primary side. Since the supply voltage is balanced like the previous one in transformer connections, I can draw this voltage triangle and supply is phase sequenced as A S B S C S. So, first I will draw this is A S, this is B S and this is C S, I will draw, and A S is A 1, A S and A 1 same, B S and B 1 is same, and C S with B 2 it is also same, it is like this. So, what is the voltage applied across the primary of the transformer B? It is this one B 1 B 2. Okay. Therefore, if we say that like the previous one, these 1 1s are dots, these 1 1 are dots, suppose I say, then on the secondary coil I will have this induced voltage, which will be B 1 B 2. We have done much more complicated case in case of 3 phase. Okay. Now, here it will be like this, what else? So, this will be the secondary this voltage phasor parallel to B 1 B 2. Of course, I have not correctly named, this must be B 2 is connected to C S. So, it should be, I am sorry, this is B 1 is connected to B S and C S is connected to B 2. So, voltage applied across this is B 1 B 2. So, the secondary induced voltage B 1 B 2. So, I should name it accordingly, na? B 1 is here. So, it must be B 1 and B 2. Now, it is correct. So, this is the available voltage. If any mistake, please point out. This is the thing. like the several times we have done in case of 3 phase. Acha. Now, the question is what is the voltage applied, and this point I will call O, where that 50% tapping has been taken. Now, the question is where this point O is in this phasor diagram. It must be at the middle point. O lies here, because half of the voltage if you move from here you get O, is not. This total voltage is this VLL by 2, VLL by 2 will come here. So, this point is O. The moment I get this O point is nothing but also your A2 point, because you have connected like that. And what is the voltage applied, and this is A1. So, voltage applied across the primary of transformer A is this vertical line, is not. This is the voltage applied across the primary of transformer A. If line to line voltage is VLL, what is the magnitude of the voltage applied across A1, A2? It will be this length, this is 60 degree. So, length A1 O is nothing but VLL sin 60 degree, na, root 3 by 2. See, my goal is to get at the secondary two voltages which will be 90 degree apart. What is balanced two phase voltage? Balanced two phase voltage is like this. Phase voltages will be equal and they will be 90 degree apart. Maybe one phase is A, another phase is B. That is what I want to get. So, one voltage phasor is like this. To the primary of transformer A, I have applied this voltage, whose magnitude is VLL by root 3. Therefore, induced voltage on the secondary will be also parallel to this, that is A1, A2. I want this length to be same as this length. What is the voltage per turn? This voltage divided by number of turns of the primary. So, voltage, since secondary turns I have said to be same, I must ensure that the voltage per turn of transformer B and voltage per turn of transformer A, they must be same. So, I write that. So, voltage per turn must be same for transformer A and B and transformer B. They must be same. Then only the secondary voltage magnitudes will be same. I will simply multiply with N2 to get the secondary voltage. For this transformer, what was the voltage per turn? VLL by N1, which must be VLL by N1. Now, this voltage I have right now seen, it is VLL into root 3 by 2. Therefore, its number of turns, if you set it to capital N1 as before, its voltage per turn would have been then VLL root 3 by 2 divided by N1, and its secondary voltage would have been VLL by root 3 by 2 by N1 into N2, and that will not be same as this one. So, to make the voltage per turn same, that is why its number of turns of transformer A primary is chosen to be root 3 by 2 into N1. Then I will write, you see, voltage per turn of transformer B must be VLL root 3 by 2 divided by root 3 by 2 into n 1, and that will tell me this is VLL by n 1 as the transformer B. Therefore, the length of this phasor, length of A 1 A 2 and B 1 B 2 will be then VLL by n 1 into n 2, they will be same. So, you see at the secondary coils of these two transformers, there exist two voltages whose magnitudes are same and which are 90° apart. So, it was a balanced 3 phase voltage, and on the secondary coils, although I have not connected them yet, I get a balanced 2 phase voltage. Is that correct? No confusion. Okay, fine. Achha, if that be the case, then what I will tell is this: I will now join A 2 and B 2 to create the neutral of the 2 phase system, and I will take output 3 terminals. I will take. One will be marked as A, another will be marked as B, another will be neutral. So, the moment you join, these two phasors cannot remain in isolation. A 2 B 2, what I have joined? A 2 with B 1. Therefore, I must place this as A 1 A 2, and I have joined A 2 with B 1. So, it should be placed here. It will be like this. Or what you could do is this: if you want to make the A phase voltage leads the B phase voltage, you can join A 2 with B 2. Are you getting me? What I will do is, I will join A 2 with B 2 to create the neutral. In that case, how it will look like? Please be with me what I am telling. This is okay, fine, balanced 2 phase system you will get, and A phase voltage will lag the B phase voltage, and neutral is here. Another way you could do, connect the secondary coils. This was the thing. This was A 1 A 2, this was B 1 B 2, is not, and A 1 A 2 voltage is here. So, I could join A 2 with B 2. Did I not join that? No. Why I did not join? A 2 with B 2 I could short. Okay. So, in this case A 2 with B 2 I will short and get the output from this, getting the neutral. Therefore, let me clear this, I will do like that. Okay. So, let me slightly modify this, but you get the idea, that will also work, no problem. So, what I am telling is, this is B 1 B 2 I have drawn, these are the voltage phasors like this. So, what I will do now, I will join A 2 and B 2 together, that is and call this to be my neutral, and I will take output from this as A phase and take output from this for B phase. And if you do like that, A 2 B 2 you join, then your phasor diagram will look like A1 B1, A1 A2 and I have joined B2 with B1 and this is my neutral. That is what I mean. The earlier one will also do, but anyway let us draw like that. So, that A1 B1 supply comes out like that and this is your balanced two phase voltage. In case of balanced two phase voltage, and this I will say as the line to line voltage. Line to line voltage will be root 2 times the phase voltage, you can easily understand. So, so far so good. So, this is what is Scott connection is. So, these two transformers in terms of number of turns they are not identical. Secondary turns must be same N2 N2, but primary turns of transformer A which is just drawn vertically. This vertical drawing has nothing to do with really 90 degree this axis that axis, no. On the table you draw, I have drawn it so that I understand these phasors much more easily. So, this is transformer B having N1 turns and also I will demand a 50% tapping available from the primary of transformer B and then I will connect like this, connect it to a balanced 3 phase system and the number of turns of primary of transformer A is not N1 as that of B, but it must be root 3 by 2 into N1 okay? And secondaries are connected like this. Is that clear? So, that is the thing. Now, the question is that I will connect a balanced two phase load on the secondary side. So, I have got a balanced two phase voltage, the magnitude of the voltage also I know. So, I will connect a balanced two phase load here on the secondary side. So, some balanced current will flow. Then how to estimate the current which will be drawn from the supply, 3 phase supply, that is important, is not. I must examine, because after all you see you are connecting a balanced 2 phase load, here is a 3 phase system, 3 phase voltage supply system here, will like that it also supplies a balanced 3 phase current, not a unbalanced current like that. So, if you connect a balanced 2 phase load on the secondary side, does the primary side current which is drawn from a 3 phase supply remain as a balanced 3 phase current, and how the magnitudes of this secondary current and primary current will be related to. That will be the next thing. Suppose you have connected a balanced 2 phase load. So, between A and N, so this is the balanced 2 phase load of same magnitude of impedance. Okay? If it is Z2, this is also Z2 per phase impedance, got the point. Now, suppose it supplies a current I A, direction of the current I have assumed. So, I A here depending upon the power factor angle of Z2, it will be positioned. So, I A may be there, this is I secondary. What is this angle? Is the power factor angle of the load, is not A phase current I A. But the moment it supplies a current, these are transformers. So, rules of transformer must be satisfied. What is that? Voltage ratios are in the ratios of turns. Similarly, if through the dot a current comes out, its primary will draw additional current through the dot, whose magnitude will be I A by turns ratio of this transformer. For transformer A, I am telling. So, it must draw an additional current I A dash, whose value will be I A divided by what is the turns ratio? Say turns ratio of transformer A is how much? Root 3 by 2 N 1 by N 2. So, I A by A turns ratio of the transformer B. So, that is how it will be reflected upon. Okay. So, this is I A and this is I A dashed, which is the line current of F S happens to be. So, F S current will be also in phase with this, that is what we have learned. So, primary side F S current, if I show, it will lag, I mean it will be in same phase. I am just drawing here, it does not mean any connection etcetera, current I am drawing. This is your I A S, which is same as, which I am calling it as I A dashed. This will be thing and this angle will be theta 2. So, the line current of the primary side I have drawn, but there are two other line currents. Let this line current be IBS, that is how in a 3-phase system I show, let this be ICS. Okay. Now, I must find out in terms of the secondary current what will be the value of IBS and ICS. So, same rule, that is MMF must be balanced. Now, in this case it will be slightly tricky in the sense that this current, suppose this current I say this is I small b secondary line current, through the dot I b current is coming out. Therefore, there will be reflected current here on the primary side, and that reflected current in terms of IBS and ICS, if I write, I will balance the MMF. Here also I could do like this, IAS will be such that, see this is I have followed, but I could write it like this, IAS, the value of IAS I could calculate, the MMF produced by primary root 3 by 2 into N 1 must be equal to I A into N 2. Same thing I will get, this is I A S is I A dash, if you bring it down here the same thing you will be getting. Got the point? This one N 2 root 3 by 2 N 1 by N 2 is A. Similarly, I will balance the MMF of the secondary and primary for transformer B. Now, let me write only on this page, let it be clumsy, so that we do not miss the point. What is the MMF produced by transformer B? Current coming out from transformer B is how much? IB. So, IB into N 2, IB into N 2. Therefore, through the dots currents will go in, but you see here there are two halves of this N 1 having the primary having total N 1 turns, of which N 1 by 2 turns is carrying IBS current entering through the dot. Therefore, this MMF must be equal to, let me write here only, so that you understand. So, this must be I B s into n 1 by 2, that is the thing. But this portion is n 1 by 2, but it is carrying current. See, if this is dot, this is dot. So, this plus, so current flowing into the dot of this part is minus I C s into n 1 by 2, and this should be equal to I B into n 2. See, this is crucial. See, secondary MMF through the dot I B current is coming out. So, I am just telling. So, through the dot current is coming out. So, I B into n 2, this is the direction of I B I have assumed. So, through the dot if current comes out, in its primary, through the dot current will be invited, as here was small I A through the dot, here there was no complication only, but here these two parts carrying different currents. So, I have to calculate. So, through the dot current coming out is I B. Therefore, I must expect through the dot what is the current flowing. I B s by virtue of its direction enters through the dot, but that I B s lasts for only n 1 by 2 terms. So, it is I B s by n 1 by 2 I have done. Through this portion of the coil, I have assumed I C s flowing like this. That is what we assume for 3-phase circuit analysis. And if this is dot, this is dot, we have learned in auto transformer this that. So, current flowing in this direction is minus I C s. So, this plus minus I C s into n 1 by 2, and that must be equal to I B into n 2, or this is equal to I B s minus I C s is equal to I B into n 2 by into n 2 by n 1 into 2, is it? This is crucial. This is the thing we get. See what my problem, what is the statement of the problem? Statement of the problem is, okay, you get a balanced 2-phase voltage, connect a balanced 2-phase load, secondary currents which are balanced, this will be I A, where will be I B? 90. I will make it more clumsy on the same paper, so that you understand. I B will be here of same magnitude, lagging the B phase voltage by theta. These two I know. What I am trying to do now, then for this loading, what should be my I A s, I B s, I C s? Directions I have assumed in accordance with the 3-phase circuit directions. Then what should I do? I must balance the MMF. I will neglect the no load current, etc. So, write the MMF equation here. What is the current coming out through the dot I A? What will be the current coming in through the dot? It is I S, it has to be. So, these two MMFs are same, because they will nullify the flux. So, that is the first equation, I A s into root 3 by 2 into n 1 is equal to I A into n 2 over. But for this portion, it is slightly, you have to be careful. The current direction I B I have assumed like this, coming out from the dot I B like this. So, I B into n 2, that is the secondary side, then through the dots must current enter, and that MMF I have to calculate. Now, IBS enters through the dot. So, IBS, but this IBS is up to this point n 1 by 2. So, IBS into n 1 by 2. Now, what about this portion? You have assumed this current to be ICS. So, I can always presume minus ICS is flowing and this is dot. So, this MMF plus this MMF must be equal to this. So, this is one equation. IAS in terms of secondary currents I have already calculated. IAS was how much? I have calculated. See, IAS already I have got 2 by root 3 into n 2 by n 1 into IA. So, I have to find out the 3 phase side current in terms of secondary current, of which IAS already obtained. Now, I have to find out IBS and ICS in terms of secondary currents. That is what we are planning to do. To do that, I find another equation is missing, because I must have two equations in order to express IBS and ICS in terms of secondary currents. Okay, this is one equation. So, where is the third equation? Third equation is, it is a 3 phase system, IAS plus IBS plus ICS must vanish to 0, or the other equation is IBS plus ICS is equal to minus IAS. Right hand side is known, IAS has already been obtained. I will put it here, then I have two equations, I will just simply solve them. We will continue this discussion in the next class. Thank you very much.